equation, h of t, let's make sure we know what each variable represents. So here, what does the t represent? The time after it's dropped. What does the h represent?
Height.
The height of the penny. So neither one of these is speed, right? Time and height. So let's find these values. So do you guys know a good way if you're given a function to plug in values to find their output?
Yes.
You could put in your calculator. Yeah. You could go y equals.
Wait, we used to.
This is exactly what we practiced
The other day.
the other day that we took all class to do.
How often do you have to charge these guys?
Maybe every other week. I don't know. Maybe it's every month. When I had these, when I used these in school, it was not rechargeable. We had real batteries we took in and out, so I don't have a good gauge. I know them. They would normally my class would let it run until it went dead, and then whenever it went dead, they would come in here one day and switch out with these during class time and then take theirs back. That's fine if you want to do that, if it runs dead, because it has a charger on the bottom.
Plug it into the wall?
Well, you do, or you have to have those special, or to your Chromebook. Yeah, I mean, any USB will work. You type that equation in. So once I've got it typed into y equals, I'm going to click second mode, which is going to be quit. It's going to go back to the main screen. You can go alpha trace and then plug in whatever you want to plug in. So I plugged in 0 and I got 1250. Alpha trace, plug in 2. I got 1186. Is everybody doing okay here?
No. I got 0.
Okay, did you click y equals?
I did it on what? I don't think it'll make it enough.
What did you get when you plugged in 4?
994.
994.
Don't even make it enough.
It's already on the ground. Everybody good with doing these three like that? I'm going to show you a different way you might do this one. I probably wouldn't do this one by the way we're doing it on here. There's actually a quicker way when I'm plugging in multiples like this. So if everybody will click second and click window, that's the second button at the top. It should say table set when you click second. Okay? And mine has a thing that says table setup that's popped up. So let's start our table at 0. And then let's go delta table is 1. So make sure you get 0 and 1 on there. And then it should be auto for independent and dependent. Okay? Then once you're there, click second. Click graph. And you should have a table of values. They're popping up. And so you see where it's 0, 1, 2, 3, 4, 5, 6. You're plugging in all those different X values. Yeah. So if I need to plug in 6, what was the output? It was 674. And if I plugged in 8, it was 226. All right, so that one, the table is probably a little bit quicker here because you've got so many you're plugging in at once. Questions there? 2, can we find an exact time when the penny reaches the ground? We know about when the penny hits the ground. You guys told me it was before 9 seconds, right? So how could I find the exact time it hits the ground? Well, what can we say happens when it hits the ground? What reaches 0? The height is 0. Do I have a variable that represents height? H. So I'm looking for t when I know h is 0. So guess what we can do? We can plug in 0 for h. So that tells me 0 equals 1250 minus 16t squared. And now that I just have a single unknown, could I find that unknown? Can you isolate the variable? Solve? Okay, so I'm gonna do it kind of quick. I would move this one over. It would become positive 16t squared equals 1250. Everybody's okay with move it over and change its sign? That doesn't scare anybody, I hope. Divide by 16. And so I've got 1250 divided by 16. I get 78.125 is equal to t squared. Is everybody okay? This looks bad on the board. I would normally work down the page, right? But I don't have any space on this paper. And so I don't care what t squared is. I want to know t. So take a square root of that. And I would get t equals 8.8388. So let's go 8.839. We want to round to 3 decimal places in pre-cal every time. Okay? Go to 3. So let's get in that habit early.
So like if the answer's a whole number, we gotta do .0000?
No, but if it's a decimal more than 3 decimal places long, stop it after 3.
Well, I didn't know, because we had to do that in chemistry.
Yes, yeah. Oh, you had to go. That's probably sig figs. Then in science, where you had to have so many significant figures for. Again, I hated chemistry, so.
The answer wrong if it was 8.
Right. So on this one, if you put 8.8, you would miss it. If you put 8.83, you would miss it. You have to go to 3 decimal places. But that's only because there's numbers there. If it was all zeros, we can ignore. Or if it stops, like if the answer is really 8.5, 8.5, you can write 8.5. But if there's more decimals that exist, you got to go to the third one. Okay. Questions on how I did that there? Do you guys know how you could find that in your calculator? Because, okay, let's think about what we just did. If h is 0, think about it graphically. What did I just find?
How many seconds it takes to...
I did find t. How many seconds? Now, you're giving me context. That's good. And that's true. Think about it as a graph, though. Do you guys know what shape this graph would be, just when you look at it? If you don't, that's okay, because we haven't done parent functions yet.
Would it be...
Okay? If we're not sure, okay, calculator. Is everybody calculator here?
It looks like this.
Kind of. Click zoom. Everybody see the zoom button? It's in the middle at the top. And then click 6 for zoom standard. So mine looks almost like field goal post, right? Field goal post. Almost, yeah. So it's not. It's because my graph is zoomed in way too much. Okay? Because think about, what's the y-intercept here? Where does it cross the y-axis?
Wait, mine is a bunch of lines.
You don't know where the y-intercept is? How can you find the y-intercept?
Like we go to, I want zoom, Z zoom.
How do you do it?
I'll tell you
What do you have saved?
And delete all my old ones.
Yeah, where's the
That's
one
not where
that
it's
you-
supposed to have that.
Should I delete it? I think you do it.
I think, did you clear up your Y's from yesterday?
Yeah, that's what mine looks like right
No,
now.
I didn't.
If you
All
didn't-
your Y equals?
Yeah, if you didn't clear those out.
Yeah. That's what mine looks like right now.
Mine looks like a C. Or water
You
fountain.
just retype it in. Just say that's the only one. You good? Just look like this. Everybody okay over here?
There's on it when I got it. My sister must have.
So, what's a y-intercept? Tell me everything you know about a y-intercept.
Y-intercept is when the x is 0.
That's the two things I want to know. It's where it crosses the y-axis where the x value is 0. So here, when my x value is 0, what's the y-intercept?
1250.
So this needs to go all the way up to 1,250 on the y-axis. When we did zoom standard, that means we made our window 10 by 10. So this goes from -10 to 10, -10 to 10.
That's why it looks like parallel line.
Because it's zoomed in so much that it needs to be 1250. So there's two ways we can zoom out, okay? If you don't know what your window needs to look like, you can click zoom, and then you see how 3 is zoom out. So you click 3, enter, and that zooms out a little. You can see that? You can go zoom, 3, enter. Zoom, 3, enter. And it's not going to look good on this graph when I do that again. I mean, this just looks like a disaster now, right? It's zoomed way too far out. Because the X's don't need to be zoomed out, only the Y's do. That's what's messing with me. So I can set the window to be what I want it to be. You guys ever done this on here before?
Mine's
Zoom fit.
Nope.
Whenever I do zoom 3 enter.
Where do you see zoom fit?
Mine's 0.
We can try that. I've never done zoom fit.
Oh, that works.
Where?
Looks like this at the top.
It does. But like, where's my X? Where's my X's at?
Where's zoom
Where's zoom through that?
It was number 0 on that list of.
I don't
So,
have zero.
I don't
if that happens, let's try to turn it off.
Oh wait, yeah, you
Second
can. You do.
on.
It's all the way done for, right?
And she'll reset where you were and go back.
Yeah, that's the one.
So if your calculator freezes up, sometimes you may have to turn it off and back on for it to work. If that doesn't work, every calculator has a reset button on the back. And so just put your pencil in there and reset it if it won't turn off either. So if you get on test day, you need this calculator. Calculator's frozen. I can't help you on test day. You gotta know how to do your stuff. So, but I'm just making sure that's something I need to tell you that I have attention.
So it looks like this.
It does, but mine doesn't show the x-axis. Does y'all show an x-axis?
Yeah.
Yes, mine does. Whenever I did zoom fit.
It goes, it goes all the way out to 640.
Okay, mine, I did it again and it worked. I did it again and it worked.
Zoom fit.
Why can't I see
Mine
those?
was Joe's,
Why
Yours
can't I
looks like
see
what
mine?
mine did. Let's go zoom 6. And let's go zoom 0.
Zoom.
And we did it on the zoom bar. Good, yeah. I
Really?
really zoom fit, you're teaching me. So that's what mine looked like to start with. It's because we did it from the zoomed in version. So let's go zoom, click 6, go zoom standard. And then zoom 0 to go back to what you had before.
Good job, Jack.
Don't click enter, click enter. So do it again, zoom. Don't click enter.
Jack might be able to subtract.
Just click right.
Good job, Jake.
That was a genius move. He should be put on the wall of.
Good, good. What'd he do?
He
You found that?
zoom
I'm-
fit.
I appreciate that. Okay? If you ever want to change the window on your own though, instead of zoom fit, which zoom fit's a good thing to know, because I wish I could have told some students that last year that don't understand window. You can click window. You can see your X min and X max. Once I click window, that means we're going from -10 to 10 on the X axis. That's a good thing. That's what we wanted. And look at the Y's now. The Y's go from 1,250 to -350 from zoom fit, which is fine. I would have probably just went to 0 on the Y min instead of -350, but I like it. Okay, but that would be very similar to what I would have chosen the window to be. So you can manually change those values if you need to. I'm clicking graph again to go back to this. So, okay, we've done a lot. I'm just showing you a little bit of stuff with calculator, right, as we go. What was my question again? Find the exact time it reaches the ground. So, I showed you how to do that algebraically, right? We solved. Plug in 0 for h and solve. Graphically, where does this hit the ground? Like, where would I find that spot?
8.839.
Yeah, but if I didn't know it was 8.839, if I was just looking at the graph, it's the x-intercept, right? That's where the height is 0, the y is 0, is the x-intercept. This calculator can find you x-intercepts from a graph. Okay? That's what I want to show you. We got all this set up just so I can show you how to find an x-intercept. Okay, we ready? How to do that? Click second, calculate. It's above trace. So it's the trace button, C-A-L-C. So another word for x-intercept is the 0 of the graph. X-intercept, 0, root, solution. They all mean the same thing. So we're going to click 0 for 2. And then mine comes up at the bottom. You can see it says left bound question mark. That's because you could have multiple x-intercepts like this one. So we want to put up boundaries. So that way we're basically taking the x-intercept we want to find and we're going to put up, it has to be between this value and this value. Okay? So there's two ways we can list the bounds. Let's go left to right. So we want to find the x-intercept on the right because on the left is useless. So we can scroll over using the arrow to just pick any point that's to the left of the x-intercept. Some left boundary. Okay? So I'm at like 7.4. Doesn't matter where you are, but that's where I'm at. Okay? And I'm going to click enter. So that's one way you can list boundaries, is you can scroll. Okay?
Can we go one outside of the?
You'd have to go to the right by scrolling. I'm going to show you a different way you could do it besides scrolling though. We know what's a number that's going to be to the right of the x-intercept? 10 for sure it is. So if you want to, you can just type in 10 for the bound.
Where?
How do you
Just type 10.
Oh, x equals 10?
No, yeah. Once you just start typing 10, it'll automatically say x equals 10. And it's picking a right bound for you. So if you don't want to sit there and scroll the whole time, if you kind of know the window, you can pick the left bound and the right bound. So I click enter after 10. It tells me to guess. Guess means absolutely nothing. Okay? That's just, if you want to, that's just a safety thing. If they're...
Wait, so
Just-
what number was that? What was that?
Enter. After I put 10,
No, how do you get to the 10?
I just type it.
Oh, you're
To the right bound.
I'm at the left side.
So left bound, just pick any number to the left that you want. There you go. Equals. Enter. And then something on the right. Perfect. And then guess, just click enter. The reason guess exists is if you put up boundaries, but there were still 2 or more x-intercepts in your boundaries. Then the guess lets you, it'll pick the one that's still between there. It's closest to what you guessed. Okay, if you have multiple. If you do a good job picking your bounds, that's never going to happen. So that's why guess is really kind of useless. And I click enter again after guess, and it tells me the 0 is at 8.8388348, which is what we found algebraically, graphically. You going to remember all this? Probably not right off the bat, okay? But I just want you to see what all is possible, right? And you'll kind of, hey, can we do this? Maybe we can do that. And we'll just keep practicing with these as we go. Sorry, sidetracked. 3. What's the, oh gosh, what's this?
A-rock.
What am I thinking when I see A-rock?
Slope.
Slope, boom, slope, 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 slope. So A-rock is the change in y over the change in x. In this case, that would be the change in height over the change in time. So how much did the height change of the penny?
Drastically.
How much? Drastically is a good adjective for it.
1250 to 0.
So how much of a change is that?
1250.
1250. See why I didn't want to plug in y2 minus y1? Because we kind of know what those are. What's the change in time? How long did it take the penny to drop 1,250 feet?
8.839 seconds.
And so this is my average rate of change. This is the slope. Could you have went through the whole formal definition and did y2 minus y1? You could. You could have done 1250 minus 0 over 0 minus 8.839. Oh, that's a good point. Because the height changed in a negative direction. See, I call it an error that I made. This should be negative 1250 is the change in height, not positive. So it's a good thing I went ahead and wrote that out. So if I write it like this, I get in my calculator, let's see, second quit, negative 1250 divided by 8.839. I got negative 141.419 feet per second. So on average, the penny fell 141 feet every second. Cool. All right, 4, determine how many feet the penny fell during each 2-second interval. So we're doing equal changes in the input. You see how every one of these is plus 2, plus 2, plus 2? Now let's see, do we have equal changes in the output? So how much did we change to go from 1250 to 1189? 64. Yeah, it should be 1186. I said 1189. So it fell 64 feet in the first 2 seconds. So was that faster or slower?
That's
Slower than the A-Rock, okay? What about from 2 to 4? 192, I think. That one's a little bit faster than the A-Rock, right? And then the next one was 320. Is everybody okay with how I'm finding these values, even if we're not doing the math? 320 feet, and then 448 feet. So equal change in input does not produce equal change in output. So what does that mean? If equal changes in the input do not create equal changes in the output. What if they did produce equal changes? What would that mean?
That was falling at the same speed every time.
Which means, mathematically,
It's linear.
it's linear.
But it's not.
This one's not linear, right? So I could say this is not linear. Equal changes in input produce equal changes in output. That means it's linear. It has the constant rate of change, like what you guys were saying. I just wanted you to say it's linear, right? Tie it all together. So here, because they don't produce equal changes in the output, I can say this graph is not linear. Okay.
Wait, how much miles per hour is that?
You'd have to convert. I don't want to do it right now. You know how to convert from feet per... You ever done dimensional analysis in chemistry? You have to go from feet per second to miles per hour.
Is that stoichiometry?
Yes, I think that's what it's called.
Can't get it.
I will do a little bit of it eventually, but right now I don't want to spend time. I'll make it where you can do it, I promise. Right? I don't know what you've been told before, but it's not too bad. As long as you know.
It's easy work.
I'm going to try to make it easy. But not right now. 5. So, what was the average rate of change over each interval? So, over the first 2 seconds, we changed 64 feet. So, how much did it change every second then, on average, between 0 and 2? Right, and because we're going negative, that means it's a negative 32 is the average rate of change. The reason we didn't put negative before is because it already had the word fail, right? Fail implies a negative. So what would be the average rate of change from 2 to 4 if it fell 192 feet from 2 to 4? That would be negative 96. Is that right? 96? Okay, what about 320 here? That would be negative 160. Everybody know where I'm getting these numbers from?
No.
I'm basically doing average rate of change. But I've already know the change in Y. That's what I found right here. Right? This whole, okay. So like for 6 to 8, I would want to do Y2 minus Y1 over X2 minus X1. Right? To find the average rate of change. So let's just work this one all the way out. You don't have to do this if you understand what we're doing. What is Y2 here? So at 8 seconds, what was the height? 226. Minus, at 6 seconds, what was the height? 674. Over X2 is 8 minus X1 is 6. Right? You okay with how I came up with that? Average rate of change from 6 to 8. Now, what is 226 minus 624? Well, that's what I just got done doing here. Right? We were finding how much did it fall. So, this is negative 448. The denominator is going to be 2. So what we've been doing is just taking this value and dividing it by 2 and make it negative. Right? That's how I was doing it quickly. I wasn't doing all of this every time because I've already found y2 minus y1 here, right above it. And then x2 minus x1 is 2 on every one of them. So I'll just divide by 2 every time. Just doing slope formula a little quicker. This one should get negative 224. So essentially, I don't like it being written like that for the first time. Just you don't have to write this, just watch. So did I have equal changes in the input? Did that produce equal changes in the output? We went down 64, then we went down 192, then we went down 320, then we went down 448. So because it did not produce equal changes in the output, it was not linear. But what if I look at the change in the change? The change of the change. So like right here, I went from negative 64 to negative 192. So how much of a change was that? I got 128. Are we okay with that? then what if I went from negative 192 to 320?
128.
Oh, this one also went down by 128. Then what about from negative 320 to negative 448? So what I essentially found here, this was my rate of change, right? Over 2. This is the rate of change of the rate of change. So remember, we talked a little bit, maybe it was Monday, about what if the function was linear, that means the rate of change was constant. If it was constant, what was the rate of change of the rate of change? 0. It wasn't changing. The rate of change of the rate of change was 0. If it's a line to start with. We found out this was not a line, so its rate of change was not constant. But if I talk about the rate of change of the rate of change, it's not 0. But what could you say about the rate of change of the rate of change? We could say it's negative 128, but that's just a arbitrary value. It's constant. So this time the rate of change of the rate of change is constant. What this is called, to go from here to here, this is called the first difference. So my first difference wasn't constant. But to go from here to here, this is called the second difference. Okay? And the second difference was constant. If the second difference is constant, that means this is a degree 2 polynomial. Well, I already kind of knew that this time because it told me the equation. Does everybody know what degree 2 means? The largest exponent that exists. And so here the largest exponent is 2, t to the second. So it's a degree 2 quadratic. And so that shows itself when you look at the second difference. Every degree 2 polynomial will have a constant second difference. Every degree 1 polynomial will have a constant first difference. It's linear, which means its second difference is 0. Right? So, okay, we're kind of building up to it. You don't have to know all the ins and outs of that yet. 6. Is the penny speeding up, slowing down, or falling at a constant speed?
Speeding up.
It is speeding up. How do you know?
Because the higher A rock is going further.
So these are the ones that's a little hard to explain. We would say the A rock, I liked you using that. The A rock over each interval is getting... So what's happening to the A rock for each interval?
It's getting bigger.
It's not, though.
Wow.
That's why you got to worry about your wording here.
It's getting smaller, right?
It is getting smaller, but it's not getting smaller towards 0.
It's getting smaller towards the negative way.
Yeah. So the way we can say that to fit this, it's getting more negative.
What?
The A rock went from negative 32 to negative 96 to negative 160 to negative 224. So that's getting more negative. You not okay with that?
Huh?
You not okay with that?
Well, I was just wondering why it's negative, but it's because it's smaller.
Yes. Because it's the change in height, and the height is decreasing. That's why if it was a rocket being launched, it's easier to see. The A rock is growing, we're getting faster. Here, the A rock is decreasing, but we're getting faster because it's getting more negative, right? If the A rock was going from 8 to 6 to 4 to 2, There the AROC is decreasing, but it's getting slower. Because it's getting closer to 0. Right? Here the AROC is still decreasing, but we're getting faster. Because it's getting more negative. So it's not good enough to say the AROC's decreasing or the AROC's increasing. You have to tell what it's going to. So that's why we say it's getting more negative, or it's getting less negative, or it's getting less positive or more positive. Right? That way you can it's easier to explain. Because the negative matters here. Anyways, let's graph this. Graph y equals h of t. You kind of should already know what this graph looks like. Okay? But look at the window. What is the lowest x value this takes on? 0. So where is my graph going to start?
1250.
At 1250. And then we know at 8.89 or 8.839 it's going to be at 0. Right? Somewhere here. But is it a line? Is it falling linearly? No. So for now, we don't have to be really exact on these other points. We could, I guess. I guess we know at 2, it's 1186, which is about right here. At 4, it's 994, which would be about right here. At 6, we're at 674, which would be somewhere here. And then at 8, we're at 226, which would be here. And so that'll give me a little bit better shape than what my freehand was going to do, right? Having those points. That it's basically half of a parabola, right? It's curved. Okay. Now here we're going to be introduced to a new idea called concavity. Concave up or concave down. It's really, if you have the graph, it's as simple as looking at it like this. If it looks like it would hold water, right? Something like this, it's concave up. If it looks like it would repel water, concave down. So this one is
Concave down.
concave down. If you think about the idea of tangent lines, right? If I were to draw a tangent line here, it would look like this. A tangent line here would look like this, right? So the slopes of the tangent lines are getting more negative. When that happens, it's concave down. Okay? When the slopes of tangent lines are decreasing. So it says give context to this situation in terms of the problem. So because it's concave down, that means the rate of the pennies, the rate of change, I don't like the way they worded it. I'm going to change it. The rate of change of the penny's height is decreasing. Or in other words, the slope are getting more negative. And we can visualize that when we think about slopes of tangent lines. It's getting more negative each time I draw a tangent line to the right. It would be steeper and steeper and steeper in the negative direction.